Hello everyone, I'm Arun Joshua Kennedy, and in this video I'll be talking about coin change problem solved using dynamic programming. This problem is one of the classical problems asked in interviews and some entrance tests, and it is a good algorithm to have in your pocket. Now, what is the coin change problem? In Geeks for Geeks, the problem statement is given as: if you are given an integer array of coins of size n coins are given, and uh, of different denominations, and integer sum. Here I'm rephrasing sum as the target in my in the future uh, present the future slides, and the task is to count all the combinations of coins to make the given value target or sum. And in this problem statement, we are to assume that infinite supply of each coin denomination is available. So for example, our target is 4 and coins 1, 2 and 3 is given. Then the output will be 4 because we can have 4 solutions. We can have all ones, 2 ones and 1, 2, 1 coin of 2, 2 coins of 2s, or 1 coin of 1 and 1 coin of 3. And the same way for target 10 and coins 2, 5, 3, 6, we can have 5 possible ways to reach the target. So in lead code, apparently the same problem is slightly modified, and here we are to find the fewest number of coins that you need to make up that amount, or the target. So for if we have coins 1, 2 and 5 and the amount is 11, then we can have 2 5s and uh, one coin of 1 to reach the target. Notice that we can have all ones. That will be 11. That will take 11 coins, but we are to return the minimum number of coins. That's possible. Or -1 if it's not possible, or 0 and then the amount is 0, obviously. Now the objective on my slides, I have slightly modified it. In my presentation, I'll be showing a slightly modified uh, coin change problem, and here we are given the target and coins, and we just check if it is possible to achieve the target with the coins provided. It's just boolean true or false problem. And in my presentation, I'll be talking about two variations. Uh, one is one is infinite coins for each denomination, and the next one is finite coins for each denominations. So in the finite coins, obviously the repetitions will affect the outcome, and this is almost same as the coin change problem with finite supply that you can find in this website. It will be linked to my video. Now for infinite coins, uh, this is the pseudocode, or this is the Python code that I'll be using. Excuse me. um, Here we are initializing dp, that dp with false, and it will be one D array, obviously an array of false, and dp of 0 we are setting it as true, and we are iterating two for loops for I in range n, that is I from 0 to n minus 1, that will go through all the coins, and j, which will go from coins of I to target. And this is the formula that we'll be applying at each point, at each inner loop, and we return dp of target. Now, how will this look while executing? We have for this example, we'll be taking coins 3 and 5, n equals 2 and target equals 6. Initialize dp will look like this. First, dp of 0 is true and the rest are false. The target is 6, so the size of dp is 7, and this is dp of 6. The last element is dp of 6. Remember that. Now for coins 3 and 5, it goes the outer loop I equals 0. That is for that coins of I equals 0. Coins of 0 is 3, and j will start from 3 to 6, and start from 3 and go to 6, and this will be the state of dp after the first inner loop completes. It will be true or false, that is true, and this will be true. dp of 3 is set to true. Next, dp of 4 will be set to false because false or false. This false and this false. False or false is false. Next is dp of 5, that will be false or false is false again. But dp of 6, however, false or true will be equals to true. This um, cyan color is J, will be representing J, and this green color will be representing J minus coins of I. So true or false is true, and similarly false or true is true. Now for coins I equals 1, we go from J equals 5 to 6. Now here J dp of 5 is set to true, false or true is true. So J dp of 5 is set to true in this, according to this formula. And next, dp of false or true. dp of 6 is anyways true, so it doesn't change. And so with infinite coins of each denomination, is it possible to achieve, just possibility, is it possible to achieve 6? Yes, it is, and we written true. That is dp of 6. Now what would happen with finite coins? The finite coin Python code is literally the same. Now almost everything is same as infinite coins, but the only difference is the range for which the inner for loop runs. So here we run j from target to coins of I, so it will go backwards. Now how does it work? Let's see. For finite coins, same. We have the same denomination 3 and 5, and is obviously equal to 2 since there are 2 coins. Target is 6. dp is initialized to all false except true at dp of 0. Now here you can see the difference. Here the j starts from dp of target, dp of 6, but but in previous slides we had seen that the dp it starts from dp of 3. Cyan was here, and it moves backwards. So obviously here false or false is false, and false or false is false, false or false is false, false or true dp of 3 becomes true. And next we have I equals 1, false or false is false, I equals 1, we have coins of I equals 5. Now coins of 1 is 5, so we have uh, we have j running from 6 to 5, and we have dp of 6 or dp of 6 minus coins of 5. 6 minus 5 is 1, so obviously this false or false is false, false or true is true, so dp of 5 is set to true. Now we can see that only dp of 3 and dp of 5 is set to true. So is it possible to achieve the target 6? Obviously not, since dp of 6 is still false. Obviously with finite coins it is not possible. Now here's another example of finite coins. Here instead of just one coin 3, I'm taking two coins with denomination 3, and here we have coins of I equals 0 is 3, and obviously even this is running backwards. The inner loop is running backwards, and for 3 taking 3, the first 3 as our denomination, we have j running from 6 to 3. Obviously when j is 6, it's false or false is false. When j equals 5, it's false or false false, false or false false. When j equals 3, we have false or true, that is equals to true. So dp of 3 is set as true. Now for the next coin, this is I equals 1. That will be, so we have dp of the next coin 3, this coin. So we have true, false or true. That's obviously equal to true, since dp of j will be 6 and dp of j minus 6, j minus coins of 3, coins of 1, that is 3. So 6 minus 3 is 3 and dp of 3 is true. So false or true is true. Similarly, even this runs backwards. So false or false is false, false or false is false, and false or true is true. And this doesn't make any difference. Now for ji equals 2, we have the third coin 5. So false or true is true, obviously, since it's already true. And for j equals 5, we have false or true is true. So the final state of dp, we have dp of 0 is true, dp of 3 is true, dp of 5 is true, dp of 6 is true. So is it possible to achieve the target 6? Yes, because we have dp of 6. Now what will be the net effect of these two different algorithms? What difference would it make? Now in the first algorithm, since we have infinite coins, say if we take an example of target as 18 with coins 3 and 5, we we can achieve the target, obviously, because obviously 3 into 6 is 18, so coins of 3 would give us 18, and as you can see, many more numbers will be possible. The only numbers that won't be possible will be the 1, 2, 4 and 6 when coins 3 and 5 are given. But with finite coins, obviously 3 would be possible, 0 would be possible, 3 would be possible, 5 would be possible, 8 would be possible, but the rest won't be possible as all. For now, the summary: the only difference in these two algorithms is the is which direction j runs from. So in this j runs in positive direction from coins of I to target, and here j runs backwards from target to coins of I for each coin. And needless to say, that the algorithm that I have discussed above, they do not directly translate to the counting number of ways that's the problem. That is the problem statement given in Geeks for Geek and Lead Code. But it can be used to check, just if we want to check if it is possible, just the availability. Then we can find it using this algorithm with these two algorithms. And mm, and also we should notice that problem statement that they have given in Geeks for Geeks and Lead Code both have infinite supply for each denomination, and the algorithms will vary for infinite or finite supply. And as for the problem given Geeks for Geeks, this is the Python code with which we can solve it. Um, Obviously, for this, we initialize dp with 0 and accept dp of 0. dp of 0 is set to 1, and this will be our running loop. This will be our algorithm loop. I runs from 0 to n minus 1, and j runs from coins of I to target. And at each iteration, we do dp of j plus equals to dp of j minus coins of I. So this is how the loop would look like for I equals 0 and j equals 1. J will obviously run from 1 because coins of I equals 1. J equals 1, we have dp of 1 plus 0, 1. Again 1 plus 0, 1. Cyan would be j, and green is j minus coins of I. So 1 plus 0 is 1. And here we have next loop when coin 2 is taken. We have I equals 1, j runs from 2 to 3, and we have dp of 2 minus 2 plus 2, sorry, 1 plus 1 is 2. We have 2, and for j equals 3 we have 1 plus 1 is 2, and for I equals 2 we have 2 plus 1 is 3. So the number of ways to make the coin make the change 3. So and the target is 3, and coins given are 1, 2 and 3. Obviously it will be we can make 3 with 3 combinations. We can have all ones, 2 plus 1, one coin of 2 and one coin of 1, or one coin of 3, and that's what we have, 3 ways. Thank you.